Hey everyone, we're going to talk about the Pythagorean theorem today. And I'm going to start off by using an example from where it came from originally and how we started first using and developing this idea in history. And where it came from is something like this. In a lot of ancient cultures, in ancient Egypt and Assyria and China and all over the world, they noticed that if they laid out lengths of 3, 4, and 5, just like this, in a triangle, then anytime they did it, 3, 4, and 5, just like that, they would be forming a right triangle. And that the angle across from that length of 5 would always be a right angle. And if you've ever done any building, for example, you know how important that is. If you need to lay out a foundation, you want your foundation to be square. If you need to build walls, you want your walls to be plumb. You want them to be at right angles to the ground. So in order to develop any of the, large building projects in any ancient culture, in order to make buildings, you need some way to make right angles over large distances. This was also really important when they were developing agriculture, when they were growing things and separating out plots of land. In order to make them even and fair, there had to be right angles. And again, they noticed if they had lengths of 3, 4, 3 on one side, 4 on another, and 5 going across the third side, then all the time they'd always get a right angle across from that side. Well, eventually they started thinking about the actual numbers in play here, and they noticed, or somebody noticed something. And again, they noticed this in several cultures, but we often attribute it to Pythagoras and the Greeks, though it was noticed all over the world. But what they saw is that with those 3, 4, 5 triangles, if you draw squares on each of the sides, notice here that if this is length 3, and this is 4, and this is 5, that the squares will have an area of 9, 16, and 25. And that might not seem immediately significant. It might not jump out to you. But if you think about it, what they notice is that 9 plus 16 equals 25. And that on its own might not seem really notable or cool. But what they noticed is that there were some other patterns that they already knew about. For example, 5, 12, 13 also always made these right angles, right triangles. So they took a look at that and said, all right, 5, 12, and 13, what happens? Well, 5 squared, 5 times 5, gets you 25. There's 25 boxes there. And 12 squared, that's 144. And 13 squared, 13 times 13, equals 169. And you'll notice that it works again. 144 plus 25 equals 169. So obviously it didn't take long to sort of figure out that this was always true. That no matter which right triangle you laid out, if you took the square, if you made a square and found the area of each leg, so the a squared over here, and the b squared over here, and the c squared over here, that it would always be true that those squares on the legs, a and b, would always add up to the square on the what's called the hypotenuse, that third side, the side across from the right angle. That it would always get you that a squared plus b squared equals c squared. And the important thing with that again is that this c squared has to be this hypotenuse. It has to be the side that's across from the 90-degree angle. So let's take a look at some examples of how we can use this. So thinking back to some of the earlier uses, and we'll look at this later, it was used to find right angles. Where we're often going to use it now, though, is to find side lengths using this pattern, knowing that we have a right angle. All right, so we're looking at a right triangle. The first thing I would do is to make sure we identify which side is C, right? So which side here is C? Well, it's the side, in this case, across from the 90-degree angle. It's not always the side we don't know, but it is always the side that's across from the 90-degree angle. That's not touching the 90-degree angle. So a squared, I'm going to say that we're going to call this 2, we're going to call that A. And this 10, we're going to call that B. And x, we're going to call that c, okay? So I have a squared plus b squared equals c squared written up here. But a is 2. And notice I didn't get rid of the squared. That's still part of it. B is 10. And x that we're solving for, that's c, okay? Now it's an equation that we can just simplify and solve. So 2 squared plus 10 squared is 4 plus 100. And we should know how to solve this equation, right? Inverse operations, how do you get rid of an exponent? How do you get rid of squaring? You take the square root. So we're left with x equals the square root of 104, which you could then type into a calculator, and you'd get that x is somewhere around 10 or maybe 10.1. All right, let's try one more. So again, we want the Pythagorean theorem here. We want a squared plus b squared equals c squared. And we have to identify again which one's a, which one's b, and which one's c. And we want to start with c. We always want to start with c. That's the important one. And it's the one that's across from the 90-degree angle. It's always across from the 90-degree angle. So it's 15. A and B, it doesn't actually matter which one you pick. It just doesn't matter. Now I'm going to, because my variable is one of them, I'm going to make that A because it'll just make my equation look easier. But it doesn't really matter. All right. So we now know which one is A, which one is B, and which one is C. So we just plug in those numbers into our equation. So A, we decided that was X. B, we decided that was 9. And then C is 15. And again, just an equation, just simplify and solve. So we have x squared plus 9 squared, which is 81, equals 15 squared, and 15 squared is 225. Inverse operations to solve the equation. So we subtract 81 from both sides. And you can use a calculator if you need to get x squared equals 144. Again, we haven't solved the equation yet. We still need to get x by itself. So to get rid of squaring, we take the square root of both sides. We get x equals the square root of 144. And you might notice that that does work out cleanly to x equals 12. All right, so now I'm going to have you try one on your own. All right, so I'm just quickly going to go through and solve this to make sure you got it. That's a squared plus b squared equals c squared. The variable in this case is across from the hypotenuse, so that's c. The other two, doesn't matter which order I put it in. 4 squared plus 7, so 16 plus 49 is going to be the same as 49 plus 16. Doesn't matter which one is which for a and b. So 16 plus 49 equals x squared. 16 plus 49 is 65. Again, taking the square root of both sides gets you x equals the square root of 65. And again, that's fine as a final answer. You could also type it into a calculator and you'd get that x is around 8. Again, probably not even up to 8.1. So that's that one. One last example problem. Go ahead. All right, again, setting this one up, I notice that this is my hypotenuse. This is the side that's across from the 90-degree angle that's not touching it. So for a squared plus b squared equals c squared, that means that that's my c squared. And then the other two, it doesn't matter which one is which. You would probably want to use a calculator for this, for something with decimals or any difficult to work with numbers. I'm just going to go ahead and solve it and see what we get. I am turning into fractions since that's what's easier for me, but you don't need to do that. Okay. That's not right. Oh, right. X squared equals 36. Taking the square root of both sides gets you x equals 6.